Calcium levels in the blood are regulated by three hormones: calcitonin, parathyroid hormone, PTH, and vitamin D. When calcium levels rise, the hormone calcitonin acts to reduce blood calcium. When calcium levels are too low, PTH and vitamin D act synergistically to increase blood calcium. The thyroid gland, which sits atop the trachea, produces the hormone calcitonin, while the parathyroid glands, located on the back of the thyroid, produce parathyroid hormone. Calcitonin and PTH maintain calcium homeostasis by controlling the deposition and absorption of bone, the excretion of calcium by the kidneys, and the absorption of calcium by the digestive tract. Elevation of blood calcium levels triggers certain cells in the thyroid gland to release calcitonin into the bloodstream. Calcitonin acts to lower the concentration of calcium in the blood through its effect on bone, where 99% of the body's calcium can be found. Two cells in the bone act to regulate bone production and destruction. Osteoblasts take up circulating calcium and deposit new bone, whereas osteoclasts break down the bone and release calcium into the bloodstream. Calcitonin decreases the activity of osteoclasts and thereby shifts the balance of bone turnover to favor deposition of new bone and removal of calcium from the blood. Calcitonin's ability to regulate bone formation and resorption makes it an important regulator of calcium levels in many animals. However, calcitonin does not play a major role in calcium homeostasis in adult humans. If the thyroid gland is removed from an adult, the body is still able to regulate calcium levels in the blood. In contrast to calcitonin, the parathyroid hormone exerts a broad influence on blood calcium levels. Calcium levels are sensed by receptors in the plasma membranes of the parathyroid cells. When these receptors are activated, they inhibit the synthesis and release of PTH. A fall in the blood calcium levels removes this inhibition and triggers the synthesis and release of PTH. Parathyroid hormone acts in a number of ways to increase blood calcium. Like calcitonin, PTH targets bone cells. PTH binds first to osteoblasts, causing them to release cytokines. The cytokines increase both the number and activity of osteoclasts, thereby enhancing bone turnover. Overall, there is a net loss of bone and a rise in blood calcium levels. PTH also conserves calcium by stimulating the kidneys to resorb it rather than losing it in the urine. Finally, increased secretion of PTH causes the digestive tract to absorb more calcium from food, but this is an indirect effect dependent on vitamin D. In the kidney, PTH stimulates the conversion of vitamin D to an active form, and it is vitamin D that acts on the digestive tract to enhance absorption of dietary calcium. The lipid-soluble vitamin D enters epithelial cells in the intestines and combines with a cytoplasmic receptor, forming a transcription factor. In the digestive tract, this transcription factor acts to increase the synthesis of calcium pumps, calcium channels, and calcium-binding proteins, all of which promote the uptake of calcium by the intestinal epithelia and its transport into the bloodstream. In the kidneys, vitamin D acts with PTH to reduce calcium loss in the urine. The actions of vitamin D in bone are more complex. In the short term, vitamin D directly promotes bone turnover, liberating calcium into the blood. In the long term, however, elevated calcium levels promote the deposition of new bone and the removal of calcium from the blood. Vitamin D also acts on parathyroid cells to inhibit the transcription of the PTH gene, thus forming a negative feedback loop for the regulation of PTH. Overall, the concentration of calcium in the blood is tightly regulated by the combined action of calcitonin, PTH, and vitamin D.